Welcome to Channel 21 Science News Today. Our topic for today's broadcast is the speed of sound and light. Specifically, we want to tackle the history of the subject and give you guys watching an insider scoop about the topic. Let's send it over to Barack Obama to explain this concept. Barack? Yes, hello. Okay, I guess we'll get started right away. Alright, so throughout history, there have been many questions and ideas geared toward the elements of sound and light in the world. For centuries, people have tried to grasp these concepts, let alone actually measure them. The first known person to question the whole idea of the speed of light and whether it was infinite or not was the 5th century BC philosopher Empedocles. Almost a century later, another scientist by the name of Aristotle disagreed with Empedocles' idea, and so the argument of light speed came out of the dark. Get it? Yeah, I just can't wrap my head around the idea that something moving so fast, like light, could ever be measured. Did they measure it with a ruler or something? I have to agree that it's a very intriguing and mind-blowing topic, but keep in mind that there are other ways to measure moving particles, not necessarily with a ruler. Stay patient, and I'll be going in depth about the process later on. Awesome! Alright, as mentioned before, Empedocles started the concept and really introduced the question about the speed of sound early in the 5th century. Aristotle, on the other hand, disagreed, and so forth came the slew of experiments, theories, scientific law, etc., in order to approve/disprove the comments made by both of these scientists. So one of the first prominent individuals to actually come up with a feasible experiment to test whether light had a speed was Dutch scientist Isaac Beeckman in 1629. Despite living in a time before lasers, Beeckman realized that in order to get the results he wanted, he would have to use an explosion of some sort. Therefore, his experiment involved detonating gunpowder. Beeckman placed mirrors at various distances from the explosion and asked observers whether they could see any difference in when the flash of light reflected from each mirror reached their eyes. As you can probably guess, the experiment was inconclusive, and as the speed of the flash of light was just too fast to notice. Sorry to cut you short there, Barack Obama. We just have to take a short commercial break and we'll be right back. And we are back. Let's take it to Barack Obama once again. Thanks, Tom. And as I was saying, Galilei, just under a decade later, after Isaac Beeckman's first experiment in 1638, fell into the inquisition of the speed of light and created his own experiment as well. Galileo, like Beeckman, also suspected that the speed of light wasn't infinite and made an experiment involving lanterns in order to try and prove his theory. His experiment basically involved placing two lanterns a mile apart and trying to see if there was any noticeable lag between the two. The results were inconclusive as well. The only thing Galileo could deduct was that if light wasn't infinite, it was fast, and that experiments like his on such a small scale were destined to fail. He was also certain that light was at least 10 times faster than sound. Thanks for the information, Barack Obama. That was some really interesting stuff. Now, let's take to Abraham Lincoln to delve into the topic a little bit more. Oh, thanks for having me here today. I guess I'll get started right away. As new experiments were created and scientists were still receiving inconclusive results, a new scientist entered the scene. His name was Romer, and this was the time when the measurements actually got serious. In an experiment that made Galileo's flashing lanterns on a hill look pretty lame, Romer decided that his experiment should involve outer space. This was because he knew that he could observe longer distances since the 1 to 2 mile experiments weren't really getting that proper results. Thus, he based his observations on the movement of the planets themselves, and announced his groundbreaking results on August 22, 1676. So basically, while studying one of Jupiter's moons, Romer noticed that the time between eclipses would vary throughout the year, based on whether the Earth was moving towards Jupiter or away from it. Curious about this, Romer began taking careful notes about the time Io, one of the moons of Jupiter, would come into view and how it correlated to the time it was usually expected to be seen. After a while, Romer noticed that as the Earth orbited the Sun and in turn got further away from Jupiter, the time it would take for Io to come into view would be behind the expected time written down in his notes. Romer correctly theorized that this was because the light reflected from Io wasn't traveling instantaneously. He estimated that it took 22 minutes for light to cross the diameter of Earth's orbit around the Sun, which was later calculated at the speed of 220,000 kilometers a second. Many people didn't believe in Romer's calculations and ideas, but as he correctly predicted Io's November 9th eclipse would be 10 minutes late, everyone had to give credit to the man. Science could be completely different today if it weren't for his findings. With all Romer's help, and as time passed, the measurements started to become closer and closer to today's measurements. In 1728, James Bradley made another estimate by observing stellar aberration, being the apparent displacement of stars due to the motion of the Earth around the Sun. He observed a star in Draco and found that its apparent position changed throughout the year. All stellar positions are affected equally in this way. To understand aberration, a useful analogy is to imagine the effect of your motion on the angle at which rain falls past you as you run through it. If you stand still in the rain when there is no wind, it falls vertically on your head. If you run through the rain, it comes at you at an angle and hits you on the front. Bradley measured this angle for starlight, and knowing the speed of the Earth around the Sun, he found a value for the speed of light of 301,000 kilometers. This number is extremely close to today's acceptation of the speed of sound, and it just goes to show the innovation of humankind even in the earlier days. After James Bradley's discovery, people like Louis Fizeau decided to stray away from space and systems outside of our world and aimed at finding a precise measurement with a hands-on type of experiment. Louis shined a light between the teeth of a rapidly rotating tooth wheel. A mirror more than 5 miles away reflected the beam back through the same gap between the 100 teeth of the wheel. The wheel rotated at hundreds of times a second, therefore a fraction of a second was easy to measure. By varying the speed of the wheel, it was possible to determine at what speed the wheel was spinning too fast for the light to pass through the gap between the teeth to the remote mirror and then back through the same gap. So since he knew how far the light traveled and the time it took, he then divided the distance by the time, and he got the speed of light. Louis Fizeau's measurement was 313 kilometers a second. Another French physicist, Leon Foucault, used a similar method to Fizeau. He shined a light to a rotating mirror. The light then bounced back to a remote fixed mirror, and once again back to the first rotating mirror. However, as the first mirror was rotating, the light from the rotating mirror finally bounced back at an angle slightly different from the angle it initially hit the mirror with. By measuring this angle, it was possible to measure the speed of light. Over the years, Foucault was able to increase the accuracy of his number, and his final measurement in 1862 determined that light traveled at 299,796 kilometers. And as time passed, more and more new experiments were being made in order to solve the question at hand. Here are a few of them. In 1856, Wilhelm Edward Weber and Rudolf Kohlrausch measured the speed of light to be pretty much the same as Louis Fizeau at 310,000 kilometers a second by using ratios of electrostatic and electromagnetic units of charge in a Leyden jar, which was basically a capacitor. In 1875, Marie Cornu was able to come up with the calculation for the speed of light at 299,990 kilometers a second by improving on Leon Foucault's apparatus. As well, in 1883, Simon Newcomb used the same method and arrived at the number of 299,880 kilometers a second. In 1905, Einstein also touched on the speed of the light on his first paper on special relativity. In the paper, he established that light moves at the same speed no matter how fast the observer moves. In 1907, two scientists, Rosa and Dorsey, used the idea of vacuum permittivity and came up with the number 299,781 kilometers a second. In 1926, Albert A. Michelson used the concept of the rotating mirror by refining the techniques used by Leon Foucault and derived the speed of light of 299,796 kilometers a second. In 1950, Louis Asselin and Gordon Smith came up with a new way to measure the speed of light, which is through the use of a cavity resonance wave meter. This idea basically enabled Louis to know the wavelengths that were in the microwave cavity he was using and then extract the information from the electromagnetic theory in order to come up with the speed of 299,792 kilometers a second. In 1958, K.D. Froome used radio interferometry, which was a way to find the wavelength of electromagnetic radiation for determining the speed of light. His calculation led him to the number of 299,792.5 kilometers a second. And finally, as years have gone by, we have reached even closer to the speed of light. Today, the accepted measurement for the speed of light is 299,792.4574 kilometers a second. This was possible after 1970, when lasers were made with very high spectral stability and accurate cesium clocks. This made even better measurements possible, and C is now known as the universal standard for the speed of light. Alright folks, since we followed the speed of light and how it was derived, now let's take a look at the speed of sound and its history. Back to you, Barack. So the first scientists to actually try and calculate the speed of sound were Pierre Gassendi and Miriam Merson in the 17th century. They derived the idea for their experiment from a natural phenomenon. The phenomenon is called thunder. Since lightning comes before the sound of thunder, the scientists played on this idea and somewhat replicated the same occurrence but with a gun. They tried to measure the difference between the time of the flash of light and the sound that came afterwards, over a long distance of course. The result was 478.4 meters a second, which is fairly high compared to today's accepted value of the speed of sound, but their experiment provided a basis for ongoing and more accurate ones in the future. Progressing onwards, in 1650, Giovanni Borelli and Vincenzo Viviani used the same experiment and came up with a speed of 350 meters a second. And by the end of the 17th century, the calculations and measurements for the speed of sound were only about 1% off from today's value, all thanks to Pierre Gassendi and Miriam Merson's basis of an experiment. Also, I'd like to point out, in 1687, Newton attempted to predict the speed of sound in his book Principia Mathematica, in which he used calculus to create a purely mathematical analysis of the concept. I can't really delve into the math he did, because I'm terrible at math, of course, but I will tell you that one of the greatest scientists that ever lived actually had his math completely wrong this time. Once the evidence was there to disprove his theory, he basically smudged up the work he did to reach the speed of sound that was being derived in hands-on experiments. Wow, I can't believe it. Yep, it is true. Now, the earliest precise measurement for the speed of sound was in 1738 by the Academy of Sciences in Paris. They measured the speed to be 332 meters a second. The speed of sound today has been measured to be 331.39 meters a second at 0 degrees Celsius and 344 meters a second in 20 degrees Celsius with dry air. There are many factors that can contribute to the speed of sound, but these are the most accepted values today. The most accurate determinations of the speed of sound have been performed in laboratories, where environmental parameters could be better controlled and a larger variety of gases and liquids could be investigated. One can then derive the speed of sound from a measurement of the time that an impulse of sound takes to traverse the tube. This is the modern technique to get the speed of sound right, in accordance to the environment that it's propagating through. And there you have it, the answers to the questions about how the speed of sound and light were measured. There were many different methods and experiments that were used throughout the course of history to determine the speed of light and sound. It all started with a bit of curiosity, and now we have actually determined the speed of something that we necessarily can't even see, like sound, and we have found the speed of light, which travels at a tremendous rate. The findings of the speed of light and sound have truly made a great impact in the world of science, particularly in regards with physics, as sound and light propagate through waves. It took a great deal of understanding for scientists to theorize and experiment the topic, but all it took was a little spark of inquiry in order to start the frenzy. In the end, ingenuity prevailed, and the question about the speed of light and sound were answered. Thank you for watching today's episode, and we'll see you next time on Channel 21 Science News.